Okay, thank you so much, Mr. Kazu. I hope I'm now clear. We had started earlier at 2 minutes past 4. And I introduced myself. My name is Bakayana John, a teacher, Guyas High School Physics Paper 2. However, we have a sharing this afternoon. And like I said that, we don't have a lot of time. I wish we had, but we don't have a lot of time. So straight away, we are going into our business of Physics Paper 2. And I asked myself whether we should have a one-way I speak throughout, but I felt like I shared questions earlier. Maybe someone tried some numbers and he or she would wish to share. So in case you did any number, we are giving you first priority. We are giving you chance. Put up the hand. We don't have time. In case you tried out any number, please let us know. Anyone? Okay. As we are waiting for us to get the numbers that we tried, I will straight away go to the paper that I shared. Of course, we shall be looking at very many things, but purposely we shall go through the questions that I shared. That is the okay. Okay, I'm getting the paper. In the meantime, we say that we give priority to those who would like to discuss first. You let us know. Okay. Mm. Okay, sorry for that delay. Getting the paper. I'm trying to locate the question paper in case someone has it already. You can share. What I have is I had already filled in the guide, the solutions. Let me check. Okay. Mr. Kaziba, do you have the question paper? This I have, I already filled in the solutions. Okay. Anyone to share with us that question paper? I'm so sorry, I thought I had it here. Okay. Okay, let's share the one I have already. So we have, yes, I'm seeing a hand. Okay. We have our, are you able to see me now so that we continue? Yes? Hello? Okay, so the questions I sent, it's a full paper having all the sections A, B, C, and D. And you all know that our section A always has the theory part, has the part of light, optics, and also has the part of waves. So the parts of light in a paper that I shared has the questions that we are going to go through very fast. And then the part of waves also has the questions that we shall go through very fast. And also similar the parts of magnetism and other parts. Is that okay? So the question one had defined the following terms as applied to convex lens. I wanted to share the questions only, but I had already filled in the answers. Nevertheless, we can share very fast. So the principal axis as the point, the line passing through the centers of curvature. Yes, please.
Yes, like I'm saying, this side of ours, the screen is stuck on that folder that is having Microsoft Help Facilitation Guide and the rest.
Oh. Mm-hmm. Is it now okay? Yes. Okay. So we can continue. The questions I shared, we have them in our group. And the first question was to define the following terms as applied to convex lens. So you can access the questions actually from the group, our WhatsApp group. So the one I'm sharing here is that question and the answers that I came up with. However, I would prefer that in case you want to share anything, please feel free to share. In case you want to add on anything, the teacher is present. In case you want to add on or supplement anything, you are free. Any student, you are free to say anything. We shall be emphasizing a few or more things as per the question. So because we don't have a lot of time, we shall go straight away to the first question. So the first question is define the following terms as applied to convex lens. Maybe I want to repeat what I said, that P510 paper 2 has the 4 sections, the section 1, section A, sorry, section B, section C, and section D, where section A has both light and waves, then section B, section A has light and then waves. We have section B, section C, where we have magnetism and AC circuits, and then section D, we have current, electricity, and electrostatics. So we are defining the following terms as applied to convex lenses, that is the principal axis. And here I said that, remember I said that in case you want to share, if you did a number and you want to share, feel free. You put up the hand and we'll give you the chance. But we shall not wait. In case no one shows up, I will go through the numbers with us because I have them here with the solutions. Is that okay? Yes. So principal axis, when we draw our lens, we know that a lens has two principal foci, not so? Has two principal foci because it is made out of two glass spherical materials. That means that it comes with the two centers of curvature. That's why we're saying that that line that passes through the centers of curvature of a lens is what we call the principal axis. So if I'm to draw something, let me see. What I'm trying to talk about is this. So if you happen to, of course, each circle has a center. These are glass materials that if I happen to get rid of a part and also this part, what I remain with is simply a shape of that nature. So a lens happen to have two centers. Each center, remember, comes from the two sides of the circle. So the two centers, the line joining the two centers, C1 and C2, is what we call the principal axis. Is that okay? So, okay. So from the optical center of a lens, up to the midpoint of a lens is the distance called the focal what? Called the focal length. Altogether, so we have a point midway between the optical center and the center of curvature. That point is called the principal focus. So the distance from the optical center to the principal focus is called the focal length. I think you know that this distance, the distance here is also the same as the distance here is also the same as the distance from the principal focus to the center of curvature. Is that okay? Okay. So focal length, just like we've said, the distance between the optical center and the principal focus. I remind us that in case you want to say anything, feel free. In case there is a number that you tried out, please feel free to share. Is that okay? Okay, so we continue. A finite object is placed between the principal focus and the optical center of a converging lens. One, they're asking us to draw a ray diagram to indicate the image that is formed. A ray diagram to indicate the image that is what? That is formed. Okay. So we all know that when you place an object between the optical center, which we called the optical center, which is this one, and the focal point F, what kind of image do you expect? We expect a, yes? What kind of image do we expect if the object is placed between the optical center and the center, the optical center and the principal focus? Yes? So the image expected is going to be, of course, by reconstruction, we come up with a magnified and also virtual what? Magnified and virtual image. Is that okay? Any questions so far? Yes? Okay, if there is no question, we can continue. So use the ray diagram to derive the lens formula. Use a ray diagram to derive the lens formula. Now, in this, I was very specific. Use the ray diagram. They didn't say use a ray diagram in the past, maybe part Eroman 1. So meaning that it was not a must that you should use the very ray diagram that you drew the other time. So that's why I chose to use a different ray diagram. That is having an image, having an object somewhere along the principal axis. Of course, we know that the ray of geometrical construction, the ray that govern geometrical construction, rays that are parallel and close to the principal axis converge through the principal focus. And rays that go through the optical center are undeviated. Is that okay? So here we shall consider, now we have two triangles. We have triangle. We have triangle A prime, B prime, and C. And we have another triangle A, B, and C. And in math, you learned about the similar triangles, not so? So the formula for similar triangles is that once you divide the dimension of, once you divide this dimension by okay, the dimension of the image by the dimension of the object divided by the dimension of the image distance by that of the object distance. The ratio are supposed to be the same. So in other words, if we say A prime, B prime, out of these are supposed to be lengths. So when you get length A prime, B prime out of length AB, should be the same as length CB prime. I think that is the image distance out of length CB. Is that okay? All together? Okay, so can we identify any other triangle? So we see another triangle, A prime, B prime, these are lengths, divide by AB still is equal to FB prime, that's another length, FB prime divided by CF. So we have another triangle in this. We have A prime, we have A prime, B prime divided by AB, which is our object height, is equal to FB prime divided by what? Divided by CF. Where is CF? Okay, CF is from the center up to the focal length. I think I need to check on that. Okay. So what happens after? Okay, what happens after is that when we divide the A prime, the CB prime divided by CB, where is CB prime? In other words, we find that we have the CB prime is CB prime divided by CB prime divided by CB out of FB prime. Where is FB prime? Divided by CF will be the same as having CB prime divided by CB, which is, so what is the length? What is the length FB prime? FB prime is the same as CB prime minus CF. Not so? Because we are interested in generating or coming up with a focal length. Okay. We have CB prime minus CF. CB prime minus CF gives us FB prime. So down we are saying that if CB is equal to, where is our CB? If CB is equal to U, the object distance, and CB prime is V, the image distance, then CF is going to be F. So CF is going to be F. So you want to get the distance from the focal length up to, where B prime is. All together? So can we relate? CB prime was the image distance from the lens to where the image is, and also CB was the object distance from the lens up to where the object is. Then that is equal to the CB prime, which we said is our image distance minus the CF. The CF is the focal length, not so? So out of CF, which is focal length. So when you simplify this one, UV, when you simplify, you will come up with our formula, UV is equal to FV plus FU, of which if you divide by FUV, you come up with the length formula. Is it okay, or I repeat? Yes? Yes, please. Okay, someone is saying that I repeat. Let me get a PDF format, because this one keeps disturbing me. Okay. I think it's still a PDF format. Okay. There are many ways of deriving the length formula, and we are saying that one of the ways is by considering the object distance and the image distance. So I'm considering the approach of where we have similar triangles. For example, so if this is our okay, I hope you can see me now. Yes. So for example, if this is our we have our object distance, and then we have our image distance. So let this A prime, B prime, and C, and then A, B, C, be two triangles that are similar. Of course, like I said, that you can have rays that are close and parallel to the principal axis. We know that after reflection, they go through the principal focus. And also the ray that goes through the optical center goes through undeviated. So we are saying that we have with us similar triangles, of which we have one of them, A prime, B prime, and C, and also ABC. So let us first consider the one for A prime, B prime, C, and ABC. Altogether, okay, someone is saying that. Why are we not using symbols for the lenses? The arrows, like, and I beg your clarification on why you used another ray diagram to derive the length formula, and yet the question has, yes, I used a different one because in a question, we didn't specify that using a ray diagram in Roman 1, in part A Roman 1 above. So you have chance to use any other. But if they specifically say that you use okay, yeah, here the question is open. You can use any other. You can use any other of your choice. So I chose this one, but we can have other ways of deriving. This one we have we have our object, we have our image, and we are saying that from the knowledge of similar triangles, we see that triangle ABC and triangle A prime, B prime, and C, these triangles are similar. Is that okay? And we know that from the knowledge of similar triangles, if I divide A prime, B prime out of AB, this should be the same as C as you relate to the diagram. Where is CB prime? From the center to B prime, and also out of CB. CB is from the center to B. So here we are relating the object height divided by the image height divided by the object height, and also that ratio should be the same as the image distance out of object distance. Is that okay? So there are other triangles. You can't hear me. Is it a general challenge? Can anyone hear me? Maybe it is the issue with your, unless if it is a general challenge. Others, are you able to hear me? Yes? Okay, fine. Fine. So we are saying that if we looked at Roman 1. Now Roman 2, we are also relating triangles A prime, B prime. You check on the diagram, where is A prime, B prime, and also F. There is that triangle A prime, B prime, and F. That triangle A prime, B prime, and F. Then we also have another triangle CDF. CDF. There is also this triangle CDF. I hope you see those two triangles. A prime, B prime, and F, then CDF. So these two triangles are also similar, meaning that I can divide A prime, B prime by A. When I divide A prime, B prime, A prime, B prime by AB can be the same as FB prime divided by CF. So we're just we are dividing, because you know that CD, the height CD is the same as AB, meaning that I can say A prime B prime divided by CD, or I can say A prime B prime divided by AB, because height AB and height CD are the same altogether. So if I divide the length A prime B prime divided by AB, that ratio should be the same as saying FB prime divided by CF. So that is our equation 2. Now from equations 1 and 2, can we try to relate something from equation 1 and 2? Where is CB prime? If I say CB prime over CB is equal to FB prime over CF. So why? Because I know that from equation 1, I have A prime B prime over AB is equal to CB prime over CB. And also in equation 2, I had A prime B prime over AB is equal to FB prime over CF. That means that I can equate the right-hand side of equation 1 and equation 2. I can equate the two. So when I equate the two from the right-hand side of equation 1 and then that of equation 2, I come up with this. That okay? Now from this one, we know that CB prime over CB is equal to, what is CB prime? CB prime, where is it? CB prime over CB is equal to, what is FB prime? How do I get FB prime? FB prime is this length. I want to, FB prime is this length, not so, which is the same as, CB prime minus CF. And also, CF, that length CF is the same as the focal length. You see that? Meaning that if I reach this step here, if I reach that step, I can easily say that CB prime over CB is going to be the FB prime, which is CB prime minus CF out of CF. So here I can just substitute. I say CB prime out of CB is equal to, this is CB prime minus CF was F out of CF, which is F. So what was CB prime? If you relate on the diagram, CB prime is the image distance. And what was CB? CB was the object distance. Is equal to CB prime still is V minus F out of F. Is that okay? So that means that if you simplify this, okay. That means that if you simplify, this is where we are. If you simplify, if you go ahead and simplify this expression, of course, when you cross multiply, you get VF is equal to UV. Okay. VF is equal to UV minus UF, of which if you make UV the subject, you come up with VF plus UF. So from here, that's where I divided by UVF throughout. UVF by UVF. So that's how you come up with that formula. Okay. Someone is asking, do you have the guide for these questions? Of course, I'm going through the guide that I made. Is that okay? Yeah, but like I said, that feel free to add in case of anything, you can feel free to share with us. So that is, I wish we had a lot of time, but we don't have a lot of time to, we would have discussed a lot. So we shall go to, yes, I'm seeing a hand. Yes, please. Should we, I think you can speak. Yes, please, Bridget. Unmute. Okay, meanwhile, I don't know what is happening with the audio, with the microphone, but we can continue. Someone might be working it out. Maybe she has sent a question in the chat. Can you share the guide? Okay. Okay, I think I'll share the guide after the session. For now, I want us to discuss. After the session, I will share. Hope I've answered that one. Okay. We go to another number, another question, or another part. Don't forget, I'm encouraging, if there is anyone who tried the number, we are giving you priority to take us through. But we shall not wait because of time. For us, we shall continue. Okay, an experiment to determine the focal length. An experiment to determine the focal length of a concave lens using a plane mirror, a converging lens, and an illuminated object. A plane mirror, converging lens, and an illuminated object. So, yes, you know there are many ways of determining focal length of a concave lens, but here we are specific that you should use a convex lens, plane mirror, and an illuminated what? Illuminated object, of which we have our setup as shown. So on the left-hand side, we have a screen. Then on the right-hand side, we have a plane mirror. Then we have a concave lens that is brought in between the convex lens and the plane mirror. Altogether, yes. So a concave lens is brought in between the convex lens or converging lens and the plane what? And the plane mirror. So the experiment is first carried out. The experiment is first carried out by, first of all, you state that the apparatus is set up as shown above, and also the wire gauze is illuminated with a bulb, and the position of the lens is adjusted until the sharp image of the wire gauze is focused on the what? Is focused on the screen. So this is before we introduce in the lens L what? The lens L2. Is that okay? So you first focus, or you first find the position of the, image before you introduce in the concave what? The concave lens. So after that, we then, who can tell us by doing so, what are we looking for? What are you looking for? Why do we first work it out without a concave lens? What is that first procedure for? Yes, please. Yes, someone is requesting that I should unmute you. I wish I can. I don't know how I can do it. I love so much that you should participate. I don't know how I can unmute. Is there a way? I don't know if Mr. Kaziba is on and to head a pass. So that people can participate. I like the question you send in the chat, but sometimes I see them a bit late. So these first-hand questions would do so good if someone has a question. But nevertheless, if you fail to say something, you can post in a chat. Once in a while, I can check through. Is that okay? Yes, please. Kata Katale Kamese, modern. Please tell us, you want to say something?
Master,
Yes?
we are looking for the focal length, which
Yes.
is F1.
Very good, very good, very good. At least I get encouraged that people somewhere are following. So we first focus the converging lens before bringing in the concave lens, and the idea is that we first get F1. Is that okay? Then after we introduce in, at least you have the question paper we sent in our group, so you can follow up the question. The guide I will share after. Okay, so after we introduce in a concave lens between the convex lens and the plane mirror, so we adjust the concave lens to and fro. We adjust it to and fro. So at a point when rays meet the plane mirror at 90 degrees, okay, at a point when rays meet the plane mirror at 90 degrees, there we expect that the object, now this is after inserting in between the convex lens and the mirror, after inserting a concave lens. So when we adjust until the object coincide with the image. At that point, rays meet the plane mirror at 90 what? Meet the plane mirror at 90 degrees. Altogether, yeah.
Yes.
So after that, what happens? Can someone guide us in the steps next? Yes. Yes, please. So we have adjusted the concave lens until the image coincides with the object. And we said, for as long as the image coincides with the object, then it means the rays from the concave lens meet the mirror at 90 degrees. So we can see that on the diagram. So after that, what next? Yes? Yes, I'm seeing a hand. Sense. Yes, please. Okay, we have adjusted the concave lens until the image coincides with the object. And I'm asking, what is next? What are we trying to find out? Yes? Okay. Okay, now you can mute. So we are saying that the distance, the relative positions of L1 and L2 are adjusted until a sharp image of the wire gauze is formed just beside O. That's what we talked about, that until relative position of L1. L1 is the convex lens, L2 is a concave lens. So we adjust, we basically adjust L2 until we have the image coinciding with the object, the image of the wire gauze. So at that point, we are saying that the distance U1, I think you know where U1 is. U1 is between the object. U1 is between the screen. U1 is between the screen and the lens. So the distance U1 and D are measured and recorded. Remember, our task is finding the focal length of what? Finding focal length of the lens, the concave lens. So how do we get the focal length of the concave lens? How do we get the value of F2? So we know that if our U is between, the screen and the concave lens, and then our V, are we listening? Our V is the distance L2 and I prime, not so? No, sorry. Our V is that, we said U1 plus D gives us the what?
U1 plus D.
Yes? Okay. Okay. So how do we get our final image? Yes? Yes? Yes, please. Please tell us. I hear some people speaking. May you please share with us? How do we get the next step to get F2? F2, the length of the focal length of the concave lens. I see a hand, a question, or you are giving us the response or the answer. Yes, Bridget. Okay. As they are thinking, let me continue. So we shall have, I don't know how best we can unmute. Okay. Okay, you can continue. Okay, if no one is saying a word, we can continue. So how do we come up with F2? F2, which is the focal length of a concave lens, can be calculated from V1 minus D. Now the question is, which one is V1? You remember how we got the first. You remember how we got the first position of the image without a lens, without a concave lens, where we adjusted the convex lens until when a sharp image was formed. Altogether. So now I'm interested in getting. Yes. Is someone having something to say?
Hello?
Yes, please.
Can you hear me?
Yes.
Can you hear me?
Yes.
Can you hear me?
Yes, I can hear you.
I want to know whether those lenses should be combined or not.
Whether they should be combined, put together. Eh?
Yes, without
No.
that distance.
Yes.
Without that distance B.
Without a distance, the distance is necessary, but even without a distance, I think you can get the answer, or you can get the expected. So, but I was asking a question, someone to take us through the final step of how to get f2, the focal length of a concave lens. Yes. Yes, I'm seeing a hand. Please, you can tell us. Yes, Elijah.
It is not measuring this view plus B, it is F equals to U. U1.
Should I continue? Seems I'm seeing. Okay, Royal College, tell us. Okay, so we can get F2. We can get F2. We can get F2, the focal length of a concave lens, from a formula U. This was supposed to be U1, I think. U1. It was supposed to be U1 minus D, where U1 is calculated from the formula 1 over U1 equals 1 over F1 plus 1 over V1. Is that right? Yes? Any question? Okay, we have some simple question here for part D. The part D was saying that describe an experiment to determine the focal length of a concave lens. An experiment to determine the focal length of a concave what? Okay, please let us keep quiet. Let us keep quiet. Keep quiet. Let us mute. You put up a hand to say something. Describe an experiment to determine the focal length of a concave lens using a plane mirror, a converging lens, and an illuminated object. I think we have seen that. Now, the other one, part D, is a calculation question. So the calculation question says, Elijah, are you able to say something? The calculation question says that a point object is placed 20 centimeters in front of a diverging 20 centimeters in front of a diverging lens, and on the other side of the lens is a concave mirror, coaxial or on the same axis with it, and of focal length 20 centimeters. If the final image coincide with a, if the final image coincide with the object, calculate the focal length of a concave. Calculate the focal length over concave lens if the distance between the lens and the mirror is 30 degrees. So we also have another full experiment. Okay, thank you so much. We also have another full experiment that we can always perform practically. In this experiment, normally it guides in determining the focal length of a concave lens, where a concave lens is introduced between the object and the concave mirror. I think you have ever tried out that. You have ever tried out that experiment. So it's not so much different from the previous experiment. Yes. Any question? Okay, we'll continue. So this experiment is not so much different from the one we have seen above, because we see that in both experiments, we have a point where the object and image coincide. So for this question, one, we note that for the image to be formed on the screen, it means image and object are coinciding, meaning that the rays coming from the mirror to the final image, the rays meet the mirror at 90 degrees. And when rays meet the mirror at 90 degrees, what kind of image is formed? Or at what point is the image going to be formed? Yes? Which color am I using? If I can use this one. Okay, so we are saying that in this experiment, where you have a concave mirror introduced in between the object, and the concave mirror, we are saying that the image and the object will do what? The image and the object will coincide. At a point where they do coincide, it means that rays meet the mirror at 90 degrees. So when we trace these rays backward, it meets the mirror at 90 degrees, meaning that we need to locate that in absence of a concave mirror, where would these rays meet? So that where this ray would come on the principal axis in absence of the mirror, that would be the image. That would be the image that is formed by a concave lens. Altogether, so we are now saying that supposing, remember I said that I shared the questions on our platform, so you always feel free to refer to the questions that I sent on our platform. So supposing our image distance is IM. Where is IM? IM is where IM minus CM. IM, where is IM? IM, the I is here, and then the M is the mirror. So if I'm interested in getting the image, if I'm interested in getting the final image distance, then I'll subtract the IM minus CM. So take note of these letters. I is the image formed by this the concave lens. Altogether, so, and that is the I gives us the final image, where the distance between I and the concave lens is our V, which is a virtual image distance. But we are saying that, how do we come up with this distance? So we shall get the distance from IM then subtract off the distance from CM. Is that okay? Then the remaining distance is the virtual image distance due to the concave lens, which is V. But we know that from I to M, IM is the radius of curvature of the mirror, because we said that when the image and the object coincide, what happens is that rays meet the mirror at 90 degrees, meaning that if you trace them back, they meet, when you trace them back, they appear to be coming from a particular point. And that particular point is the radius of curvature of the mirror. So if I say that the radius of curvature minus the distance CF, what I remain with is the value of V. So in the question we are given the focal length. I think we are given focal length, which was 20 centimeters. So if focal length is 20 centimeters, times 2, it means the radius of curvature is 40 centimeters. Is that okay? So meaning that if I subtract the radius of curvature minus 30 degrees, I get 10. So that 10 is our virtual image distance. So if I know the object distance, which was given in the question U was given as 20, and I know the virtual image distance, I can find the focal length of that concave lens. Is that okay? Yes? Yeah, you can send a message on chat because, okay, someone is saying yes. Okay, so we can go to another question. We don't have time is against us. I wish we could do some more. Okay, explain why parabolic mirrors are used in car headlamps. You know, parabolic mirrors have capacity to concentrate light, not so? By the virtue of their design, they can easily concentrate what? They can concentrate light because rays that are parallel and close to the principal axis meet at the focal point. So they are capable of directing light at a particular point due to their converging power. This is because concave mirrors are converging in nature. So you know parabolic mirrors by extension fall under concave mirrors, only that in their design, they are more curved than concave mirrors. But they both have capacity to concentrate light, or when light is placed at the principal focus, they can easily do what? Excuse me. So they can easily reflect this light to form a very wide and bright beam of light. Is that okay? So we don't have a lot of time. I wish we could go to every number, but allow me to go and pick from every section. I pick one number, the rest I'll share the guide so that we have a feel of every section. So section B, which area should we go through? Should we go through AC circuits or magnetism? There is also this section for waves. For waves. Okay, allow me to go through section. This is section C and section D. We shall come back to waves. And section C, that is magnetism and AC circuits. Then section D is current, electricity, and electrostat. So in section C, what should I go through? We have magnetism and AC circuits. Which one should I go through? Yes. Okay, fine. Let us just be a little bit faster, because this is another section that is very important. Let us just go a little bit faster. You bear with me. So sketch the magnetic field pattern. I'm going through magnetism. Sketch the magnetic field pattern. I'll also go through AC circuits. If time allows, I go through section D. Is that okay? Okay, sketch the magnetic field pattern around a vertical current carrying straight wire in the magnetic field and use it to explain the neutral point in a magnetic field. Okay, for those friends of ours who, I know all of us do magnetism and we have already started on it. So you are familiar with the Fleming's left-hand rule, not so? You are familiar with Fleming's left-hand rule? Yes. So where if we have the field from the north to the south, and then we have a current carrying conductor, the direction of the field around the current carrying conductor can be determined using grip right-hand rule. You know that. So that when current is entering into the paper, then what is the direction? Current is entering into the paper. What is the direction of the field? The direction of the field is anti-clockwise. And then current out of the paper, the direction of the field is clockwise. Okay. So if we have a current carrying conductor, like a wire carrying current into the paper with a cross, and then we have the direction of the magnetic field from the north to the south, then it means the two fields, when combined, will appear as shown in the right-hand side of the diagram. So we have, remember, we have two fields, of which one is the one above the current carrying conductor, the one above, and due to the current carrying conductor, we see it is clockwise, following the same direction as the one from the magnet, which is from north to south. So above it will add up, and then under, because under the current carrying conductor, we see that one field is going to the right, but with the current carrying conductor, the field is going in the opposite direction. So there will be cancellation of magnetic field lines. So the cancellation is what brings about the neutral point. So the force will always act from the stronger magnetic field pushing the conductor to the side of the weaker magnetic field. Is that okay? Yeah, I'm going through magnetism and AC because I saw some people do both. I just say that let us be a little bit faster so that we tap in both magnetism and AC. If time allows, we shall also go through section D, then we come back to waves. I don't know if time shall allow. But to those who offer magnetism, at least I'm giving a brief on how the two forces act on one another. The one is due to the current carrying conductor, and another one due to the field, which is from north to south. And I'm saying that on the side where the fields follow the same direction, they add up to make a stronger field. And then down where we have the field lines opposing each other, there is cancellation, leading to the neutral point. So they say that we use this arrangement to explain the neutral point. Of course, I've explained that the field is stronger on one side of a conductor where there is high concentration of field lines. High concentration of field lines, and weaker on the side of the conductor where there are fewer field lines. So the resultant force is created from the side with a stronger field line to the side with weaker field line. So I said that this conductor will be acted upon by a force from the stronger field line towards the weaker side. Is that okay? Then here they are asking us to explain the factors that affect, oh, my battery, I think, let me connect to the charger, to the socket. Okay, so I think now we can continue. So the factors that affect the force that is exerted on a conductor carrying current. So the force, a conductor carrying current experiences which kind of force? Experiences which kind of force? It experiences a magnetic force which is given by BL times I, where B is the magnetic flux density, L is the length of a conductor, and I is the current flowing through a conductor. Sometimes we also put the sine angle between the conductor and the magnetic field. Is that okay? So let's see if we consider a magnetic field and then a conductor. Magnetic field and a conductor. So the angle between the normal to the magnetic field, if we call it alpha, then alpha is simply going to be 90 minus what? 90 minus theta. Is that okay? Or simply in simple terms, we can say that if this is my conductor in magnetic field, this is the angle theta. And then this is my conductor. Then the factors that affect the force exerted on this conductor, one of them is the length of the conductor, the strength of the magnetic field, and also we shall consider a component normal to the magnetic field, a component of the conductor normal to the magnetic field. In other words, if this is our magnetic field, and then this is the angle, so if we are to resolve vertically, then this side would be a sine theta. Would be, if this is B, okay. So this side would be a sine of what? A sine of the angle theta, meaning that the factors that affect the force will be the length of a conductor, magnetic flux density, and then the sine of the angle between the conductor and the sine of the angle between the conductor and the magnetic field. Is that okay? Oh, okay, let me just finish up one number in magnetism. I will not go through the other one, so that for AC circuits, we also go through something. Let me just finish up one number for those who do magnetism. So the three factors are, the general formula for force is BIL sine theta, implying that each of the following is proportional to the force. The B is proportional to force, the I is proportional to force, the L is proportional to the force, and also the sine theta is also proportional to what? To force. So if we are tasked to mention the factors that affect the force on a conductor, they are these ones: the magnetic flux, the strength of the magnetic field, which is magnetic flux density, the current, the length of the conductor, and the sign of the angle between the magnetic field and the conductor. Okay. Now we are having a conductor, a straight horizontal rod of mass 150 grams. Of course, we are given the length. We are given the length. We are given the magnetic field is measured in terms of Tesla, that is the magnetic flux density, and perpendicular to it. So remember, if we're asked to find the current through the rod, if the force acting on it just balances. So the force acting on a current carrying conductor, we mentioned that it is always BIL sine theta. Is that okay? Now, there is something that we should always emphasize, because force is a vector quantity. It is important to indicate that force is a vector what? Force is a vector quantity. Magnetic flux density is also a vector quantity. So it is important to indicate. But now, what happens if my conductor C and the magnetic flux density, which is measured in Tesla, and it is represented by B, magnetic flux density. So what happens if the angle theta is 90 degrees? If angle theta is 90 degrees, then my force will become BIL, because sine of 90 is what? Sine of 90 is a 1. Now, if this rod is being balanced by the magnetic field, then on the other side, it will be the weight. It will be the weight of the rod. I think this is an absolute measurement of current. The weight of the rod Okay, sorry for that. We go where we are. We simply equate the magnetic force with the weight of a conductor, just substitute and come up with the current required. Is that okay? Okay, then another question is about deriving the torque exerted on yes, bro parents. Yes, please. Is someone having a question? Okay, if there is no question, now another question comes in for deriving the torque exerted on a rectangular flame carrying current carrying current. That is a torque. The screen is blank. You can't see the screen? Yes? All of us? As if I'm sharing the screen. Yeah, I think we can see the screen, yeah? Okay, thank you, thank you, thank you. So we are saying that we are deriving our formula for the torque exerted on a rectangular flame carrying current. We know that famous formula, torque is equal to NAB. I don't know how others get it, but we consider a rectangular coil of 1 ton whose plane makes an angle. I think I can explain from the diagram which is here. Okay, we have a rectangular coil, which is PQRS carrying current. So it is carrying current in the direction given PQ, and then the other side of the coil receives or has current in the direction RQ. You know that when you place a rectangular coil in between the poles of a magnet, according to Fleming's left-hand rule, that is if it is a motor, if it is a generator, we use Fleming's right-hand rule. So when we're using Fleming's left-hand rule, the coil experiences a force, which force acts in such a way that if the force acts in such a way that if this is my coil, okay, I think I should do. Okay, so if this is my 2 magnets, and then we have this is my my coil. I'm picking up from the motor. So if current is flowing in that direction between from P, Q, R, and then S, then the other side automatically it will be coming back. If this is our magnet with North Pole, then the other one is the South Pole. So applying Fleming's left-hand rule, PQ, you know the field line is coming from north to what? From north to south. So you remember that every time a field line or the magnetic field meets current at 90 degrees in accordance to Fleming's left-hand rule, automatically a force is generated. So a force is generated when the current meets the field at 90 degrees. So in any case, where we have the current, of course, these are meeting at 90 degrees, only that this is a 2-dimensional screen. So the field and the current are meeting at 91. The current and the field are meeting at 90 degrees. So we shall have a force generated still at 90 degrees. That force, okay, let me try to see if we can get this. So where we have a field moving in this direction and the current at 90 degrees to the field, then automatically a force is done what? A force is set in. This is, I'm using the left hand. This is Fleming's left-hand rule. The field, the current meeting at 90 degrees, automatically a force is generated. So when we consider the rectangular coil here, when we consider the rectangular coil, we shall see that on the side PQ, we shall have an upward force being exerted, whereas the opposite side, which is RS, we have a downward force which is exerted. So the two forces constitute a okay. Yes, friends, those of SC, we are going to go through some SC numbers, but I wanted to hint because going through magnetism checks us so that you can also try it out. It's not a simple area. It is, I mean, it's not a hard area. I'm sorry, it is very simple. Yes. So on one side, we have an upward force. On the other side, we have a downward force. And we say that these two forces constitute what we call a couple. So what is a couple? A couple is simply two forces that act in opposite direction, but are of the same magnitude. So if one force is pushing, if one is pushing upward, another one is pushing downward, this metal frame will be forced to make a turn. It will be forced to do what? It will be forced to turn. So at that point, they're asking us, they are telling us that supposing, now we go back to our question, supposing it has turned such that the angle between the normal and the field line is a theta. The angle between the normal to the coil, of course, we are talking about the rectangular coil. The angle between the normal to the coil and the field is a theta. The F1 and F2 are the two opposite forces we looked at in our sketch here. So these two opposite forces which form a couple, then we have other forces F2 and F4. Those ones we have no problem with them. They simply cancel out. They simply cancel out. So it is these two opposite forces F1 and F3 that matter because they turn a coil. So as they turn a coil, we all know that torque is given by force times the perpendicular distance. Which force are we talking about here? We are talking about the magnetic what? The magnetic force, which is B. Magnetic force, which is B. And now, which distance are we talking about? Supposing a coil has sides. Let me see how I named the sides. Okay. Okay, we are here. Consider a rectangular coil of 1 turn whose planes make an angle alpha. Okay, I talked about alpha at the other end, but the sides I called PSB and also PS. I called it B. What is PS? Okay, now I can relate. This is B, and then I call this one, that one A. So that as it rotates, remember we said that torque is the force times perpendicular. Force times perpendicular distance. So as it rotates, we shall consider the perpendicular distance, which is our force is here, but now the L is the length of the coil, which is going to be the L. This is our current I. So the L is going to be the length of the coil now. And then the perpendicular distance. What is going to be the perpendicular distance? It's going to be we want to resolve this side. I want to resolve that side QR, which is the same as PS in length. We want to resolve it along along the field. So along the field, it is going to be what? Along the field doesn't come out so well, but supposed to be A cos theta if we resolve it along the field. So, meaning that the component of the perpendicular distance along the field is going to be is going to be a cos what? A cos theta. So our perpendicular distance is a cos theta. So, but we know that the b times a, if you consider this rectangular plane, the b times a is the area of the what? The b times a is the area of that rectangular coil. So, meaning that our torque is going to be the magnetic flux density, which is the measure of the strength of the magnetic field, times the current flowing through the coil. Now we said that the length and the width gives us the area, and also we can put this one. So the cos theta depends on whether the angle is between the field and the normal, or whether the angle is between the magnetic field and the coil, or whether the angle is between the normal to the coil and the normal to the coil and the field. Yes. So we shall not go into details of, but you'll find in some questions or in some derivation, the final end result is a sine. It depends on the angle. Which angle are they determining? Is it between the normal to the coil and the magnetic field, or between the plane of the coil and the magnetic field? It depends. But we shall not go into the full details. At least you know that the cos theta came in when we are resolving to find the perpendicular component of side A, which we got as a cos theta. And when we combined B times A, it created, or doesn't create, but gives us the area of that rectangular coil. So our formula becomes torque equals B cos theta. And supposing, remember all this, we considered a coil of 1 turn. If a coil has any turns, then it becomes NB cos what? NB cos theta. Is that okay? NB cos theta. Sometimes they can rewrite it as NB cos theta. I say that don't just cram the cos theta. They always put into consideration depending on where the angle is, whether it is in between the field and the normal to the plane of the coil, or between the field and the plane of the coil itself. Okay, I'm coming with SC. We are finishing this one shortly, don't worry. Please stay calm. Okay, so now they're asking if in that very formula, which we have as our torque is NBA I cos theta. So if theta is 0, that means that that means that the plane okay, if theta is 0, what are you going to come up with? Because we are testing time as well. When the angle theta is 0, then our formula simply becomes NAB. So here it's a matter of substituting. You are given values. You are given the number of turns. You are given the dimensions of the plane, the length and the width. You are given the magnetic flux density and the current. You can get the torque. Is that okay? Of course, when you have the dimension, length, and width, they can give you the area. I wanted to explain when do we use 0 degrees. Maybe it will be for another time. Time. Okay, someone is having a question. Yes. Yes, sir. Ajina nyumba. Yes, please. Okay. You can write in the chat. You can write in the chat. So okay, so that's what we have with force exerted on a coil, and specifically what happens when a torque is exerted on a what? Is exerted on, yes, I'll share. When a torque is exerted on a coil. Is that okay? So okay. So this we have seen that what happens if this was a question, draw a sketch showing, the question was for the previous calculation question, draw a sketch showing direction of current, field, and torque. The question was, let me check. The question was, a narrow vertical rectangular coil is suspended from a middle of its upper side with its plane parallel to a uniform magnetic field. Yes, I wanted to explain the concept of where the angle theta is 0. So theta is 0 if the plane is parallel to the uniform magnetic field. When we resolve, theta is going to be a 0. Of course, there are conditions when we are supposed to use a sign. So when we are supposed to use a sign, then theta will be 90 degrees, and sine of a 90 is a 1. So here we use this, we got theta as 0 because when the plane is parallel to the magnetic field, angle theta is 0 and cos of 0 is a 1. Yes. And when we are asked to sketch or to draw the diagram showing what we have in the question, a sketch comes up like this. So we are having the plane of the coil parallel to the magnetic field. So we expect maximum torque or maximum field when the plane of the coil is parallel to the magnetic field. You can take note of that. Is that okay? Okay. We skip this one. Number 6 is magnetism. Let's go through AC circuits. That is also magnetism. Okay, let's go through AC circuits. Distinguish between electrical resistance and reactance. I think we don't have a lot of time, but we know resistance deals with resistor. Reactance deals with inductor or capacitor. Is that okay? So resistance is the opposition to the flow of current in a resistor, whereas reactance is non-resistive, meaning that reactance is opposition to the flow of current through an inductor or a capacitor. Is that okay? Okay, so we have a question here. We are deriving. The question says, an alternating current I flows through a coil of inductance L. The instantaneous value is given by that, where I naught is the amplitude and F the frequency. So the question is asking us to derive an expression for the voltage V across the coil. Yes, so the instantaneous current, you know that in AC circuits, current is represented by a sine wave. That's why it is called a sinusoidal current. A sine wave is one where we have okay. Let me sketch it here. For those who have plotted values of sine theta against theta, you have always been coming up with a graph like that. That is called a sine curve. So alternating current always display or always portray the nature of a sine curve. That's why it is called a sinusoidal current, meaning that when you plot the values of values of sine against t, sine angle against angle, you come up with an expression like that. We know that the angle we are talking about in this case is the angular displacement, not so, which is given by omega t. Is that okay? Yeah. But in the interest of time, we shall not go in so deep into the explanation of that. So our task here is simply to derive an expression for. We are deriving expression for the voltage given the sinusoidal current. And we are starting from a point that sinusoidal current is given as the maximum current that flows through the inductor, sine of omega t. You know, omega is the angular velocity, not so? And omega is given by that 2 pi what? Omega is given by 2 pi f. Is that okay? Okay. Because ideally the formula would be I naught, the maximum current, sine omega t. So where omega t we know is the angular displacement. Omega t is the angular displacement. That takes us to the formula of theta, of sine theta against theta. So when you plot, of course, you come up with something like that, where its maximum value, for this case, if I'm plotting I against time, then the maximum value of this curve is going to be the peak value of the current I naught. And of course, the minimum value is also I naught, but in the negative side of the current axis. So if we are given the sinusoidal current, then by definition of voltage, you know, from inductance, the voltage is given as negative L di dt. Negative L di what? Negative L di dt. We shall not go through the derivation of this formula, but at least we know that in any inductor, the EMF induced or the voltage induced is given as negative L, where L is inductance times not times di what? dt. That is for any inductor. So I know that I have current, which is I naught sine 2 pi ft. So it's a matter of substituting where there is I substitute my expression I naught sine 2 pi ft. Is that okay? So when I substitute, what do I come up with? Show the working, please. Okay, let me show. So okay. So physical negative L d dt, where we substitute for sinusoidal current, we substitute its value. So we come up with the this was an error. That is an error. Supposed to be I naught, then d dt. Of course, when you differentiate with respect to t, when you have sine 2 pi ft, we shall have a 2 pi f moving out. We differentiate a sign, we get a cos. So we come up with We come up with that. Then state the phase of V relative to that of I. The phase is that the current lags the voltage by 90 degrees. So this expression V can also be written as V naught cos omega. Remember, omega is for 2 pi f. 2 pi f. But I was I naught. It was a sine omega t. That okay? Where V naught in this case is given as 2, we are to relate 2 pi f L I naught. Is that okay? Yeah. So from there, you can even make F the subject. F becomes V naught out of 2 pi L I naught. This formula is used somewhere. Is that okay? So now when you plot these two graphs, the graph of I and the graph of V, you see that one will be leading the other by 90 degrees, because if I'm expanding V in terms of I, then it is going to be okay. This V is going to be V naught. This is a cos, and we know that cos omega t is the same as sine 90 minus omega t. Am I right? Okay. So V is V naught sine 90 minus omega t. So this difference in the phase difference, or the difference in the angle of 90 degrees between the first equation and the second equation, is where we state that one leads or lags the other by the angle that we come up with. For example, here we are having 90 degrees, and then this one is simply omega t. So there we say that current lags the voltage by 90 degrees. Is that okay? Or voltage leads the current by 90 what? By 90 degrees. Is that okay? Okay, so that is the details. I think you have them in you have the details in your notes. See, you check through. So let us look at so I sketched for you the diagram to show us that whereas when you plot a graph of V against time, you see that one is ahead of the other by a phase difference of 90 degrees. For example, what we mean here, that if this is 0, our sine I was I naught, let's say sine was okay, let's simply call this one we are plotting against time. So a sine, if a sine of when t is equal to 0, we know that sine of 0 is a 0. When t is equal to 0, sine of 0 is what? The V was V naught cos omega t. Okay. So this one does not necessarily start from a 0. I think we can resketch it. I will correct that. So what happens for current when time is equal to 0? This begins at 0, And of course, it continues like that. And then for voltage, when time is equal to 0, the cos of 0 is a 1. So the voltage will start with a maximum value. Voltage starts with a maximum value, whereas current starts with a 0. And so voltage will begin from here. And then we have something like that. So at every point, you realize that when voltage is 90 degrees, which is pi over 2, current is 0. And when by the time current reaches 180, that is pi. Okay. Voltage is what? By the time current reaches 80, voltage is already. Can I repeat? Make it a bit clearer. Okay, so a sine curve will be like that, whereas a cos curve will always be start from the maximum value and then drop like that. So meaning that at a time when the current is 0, voltage will already be maximum. Voltage will already be maximum. And what happens when the current attains maximum value? When current attains maximum value, voltage will now be 0. So when the current attains maximum value, voltage will be at its maximum. But we shall consider a point when at the very beginning, when current is beginning at 0, voltage is already maximum. Now, when current attains its maximum value, that's when the voltage will be 0, and the difference in terms of phase will be pi over 2. So the pi over 2 is the same as 90 degrees, pi over 2 in radians. So we call that one lags behind the other by 90 degrees. Is that okay? All together? Oh, it's time. Okay, let me wind up, sorry. Let me wind up. Okay. Or there is a load that is remaining. For example, why is a coil said to be a pure inductor? And the reason is very simple, because in the process, when it is connected to the AC source, as current is flowing, energy is stored in the magnetic field, and in the subsequent quarters of the cycle, energy is released. Okay, I will share that one, I think. And then we heard about the transformer. Since it is time, allow me to stop here, and then maybe some comments. If we are given a chance another time, where do you think we can improve? Yes, please. Where do you think we can improve in just some 1-2 minutes? I've been a bit fast because time. Okay. Waves, light, we didn't do all numbers. Yes, I'm going to share the guide, but there are just a few things that I want to correct, like some spelling errors. Those I want to share. and then I want to correct and then share the guide definitely. Okay, I hope you have picked something, a one or two. Yes. Okay, we had a lot. We had that is section, that is AC circuits. We had section D, the current electricity, charging and discharging of capacitor. So I want to take us through through the current electricity as well. I think the other one has been electrostat. Through the current electricity, Ohm's law, potential divider, and then the potentiometer. Okay, I think that's enough for now. We can stop here. Maybe we shall get some other good time. Yes, Mr. Kaziba. Mr. Kaziba, back to you. Okay. Maybe you can unmute and say a word. I don't know if the restrictions are allowed. Otherwise, I want to thank you so much. If there is nothing else, we can stop here for now. The guide I will share, I hope you are on our forum. Yeah, I will share. Let me correct some, just spelling error, some few things, and then I'm going to share. Okay, have a blessed time.